All right, handout 3.3. Okay, just a quick recap. Right, in chapter 2 we talk about the shape of the distribution, so the graphical representation, and then in chapter 3 we have numerical measures of it. But let's go back to the shape for a moment, right? And we want to be able to use these two. You use the graph and also numerical descriptions interchangeably, right? Because all at the end of the day, these are just simply tools that we can use to describe something that is in reality. That's something that's in the world, right? So let's take, for example, income here. I'm going to use this top portion here, and there we go. Right? Income. Okay. Now, how is income distributed? Let's say income of people in the Bay Area. Okay. The true answer is nobody knows, right? Simply don't know for sure, right? We can try to collect samples and then plot it, right? So we can take a sample, right, of let's say 1,000 people, right, and then plot and make a histogram for it, right? So remember, right, to make a histogram, we have to make a frequency distribution, right? And then we can make a histogram. And suppose like right in for Bay Area, we might, right? Again, I have no idea, but we might get a distribution that looks like that. Okay. All right. All right, and that's the income, and that's going to be the frequency. So okay, so what does this tell you? This tells you that okay, well, the most people make amounts. Their income is over here, but you have few people who make a lot of money, right? So this is a skew right, right? Or you could have a distribution that kind of looks like this, right? So basically, you have a lot of poor people, you have a lot of rich people, and then there's no middle class, or there's people or just not that many people here in the middle, right? We can have distribution like this and so, right? Now, and I don't know what you would even call that, right? Okay, anyway, right? So you have different distributions, right? And now, if you have this distribution or any of these kind of weird looking distributions, we are limited in what we can conclude or what kind of information we can get. However, if the distribution is normal, okay, so or basically bell shaped, right? So you think this is like a bell, right? It's this curve here. So we call these things normal distribution or bell shaped distribution. Then we have this thing called the empirical rule that allow us to make certain assumptions regarding the data set. Okay, and good news or good thing is about normal distribution is it actually a lot of things have naturally a normal distribution. Or most things such like IQ, height, most biological things, humans, running speed. Okay? So a lot of things have a normal distribution. Okay, and then later on in hypothesis testing, we will learn even a bigger role that normal distribution plays. Okay, but for now, right, if you have a population that has a normal distribution, okay, so let's say that this is income, okay, then what can we do, right? Can we take advantage, right, of the fact that it has a normal distribution, right? Can we make some statements about it? Okay, so empirical rule states this, and now this is the details, but roughly speaking, right, we can also call this the 68, 95, and the 99 rule. Okay. All right. So then, if you want to memorize it, that's how you can memorize it. I'm not very picky on the decimals because at the end of the day, this is just an approximation anyway. So if you just want to remember 68, 95, 99, I'm fine with that. Okay. And basically, all right, we're looking at standard deviations. Okay. And so we're saying that if the population is normally distributed, what that means is from the center, okay, 68% of the data values are within one standard deviation away from each other. And then 95, right, or 95.44, right, are within two standard deviations, okay? And then 99.72 are within three standard deviations. Okay, so you can already see then that means majority of the population, 68%, right, are within one standard deviation of each other. Okay, so all right. So if we have, let's just say, I'll just make an example. So for example, right, so let's say we're talking about income, right? And you have a mu. So let's say the average, let's say that the average is 65,000. Okay. 65,000, and sigma, the standard deviation, is 5,000. Okay, so plus 1, right? So mu plus sigma will be 70,000, and then mu minus sigma will equal 60,000. Right? This is the range of one standard deviation away. So the statement that we can make, if we know that the income is indeed normally distributed, we can say approximately 68% of the people of the population have an income between $60,000 and $70,000. Okay, so that's the kind of the statement we can make. If I want to know, what's the income range that will include 95% of the people, then I would add one more standard deviation. So 75,000 will be the upper bound minus one more standard deviation. So 55,000 will be the lower bound. Okay, so let's give this a try. Right? So suppose that we know that high technology stocks has an average of 6.26, standard deviation 1.37. If the data is bell-shaped, which interval contains 68% of the earning, which contains 95%. All right, so when you start with questions like this, always sketch. So I will always give you a lot of room. You should always have paper available. Okay, so sketching really helps. So you just draw a quick curve like this, because since it tells you that it is bell-shaped, and then the average is 6.26. Okay, so write that in the middle. That is the mu, right? And then write the sigma on the side. Okay, so just get in the habit of collecting this information from the question. Okay. Now now which interval contains 68%? So I'm using the empirical rule. I know that within one standard deviation of the mean, right, this will contain it. So here is one standard deviation, right? Plus sigma minus sigma. Okay, and then I can get that. I can get these two numbers. Okay, so you do 6.26 plus 1.37, then you get 7.63. Okay, minus 1.37, then is 4.89. Okay, all right. So we can say 68% of stock, right, has earning between $4, right, $4.89 and $7.63. Okay, approximately. Again, just keep in mind these are all just approximations. Right, the empirical rule is a very quick way we can take advantage if we know the data has a bell-shaped distribution. Okay, let's add one more standard deviation. So just add another standard deviation to 7.63 minus another standard deviation on 4.86, right? That's going to give you, so we get then 95%, again, right? That's the 68, 95, 99 rule, 95%. Right, and if you want to expand, if you want to be more specific, you can say 95.44, right? But we say approximately 95%, right? 95% of stocks, right, has earnings between, right? And so if you subtract, right, you're going to get let's see, minus that 3.52. Add another 1.37, right? Then you get 9. Come on, pretty good. So it will be 3.52. So $3.52 and $9. Right, $9 and $9.00. Now, what if the distribution is not normal? Okay, so we don't have a bell-shaped curve. Okay, but do we have any rules that can allow us to make these kind of statements? Okay, so suppose that we don't know the distribution at all, right? We don't have a fancy name for it, and then we have the Chebyshev's theorem. Okay, so Chebyshev's theorem can be applied to any distribution regardless of shape. Right, and the rule itself is very basic. Okay, so here's the formula: at least 1 minus 1 over z square of the data value must be within z standard deviation of the mean. Okay, where z is any value greater than 1. Must be. Okay, so this is a pretty strong statement. Okay? And what is 1 minus? Let me write it here. So the Chebyshev theorem is saying this. Look, if I want 1 minus z squared, if I want to figure out what data value is within z standard deviation. I just plug it in, and then I can plug it in here and then calculate, right? So for example, right? So here, let me put it here. So for example, right, z equals and oh, by the way, it doesn't have to be it doesn't have to be a whole number. All right, so we can say, for example, z equals 1.5. Okay, I want to know what percent of the population is within 1.5 standard deviation of the mean. Okay, and I will use this. Right, I will use this if I don't know what the distribution is. Okay, if I know that it is bell-shaped curve, then I have the empirical rule. But since I don't, I have to use the Chebyshev's theorem, right? So I will simply do 1 minus 1 over 1.5 squared, okay? And it will give me 0.55, let's say 556, okay? That means 0.556 or 55.6%. 55.6% of data of data set, right, is within 1.5 or 1.5 standard deviation of the mean. Okay. All right. Now, what you will notice, right, that because this is the statement, right, it says must be, right, this estimation, okay, is going to be much more conservative than the empirical rule. Okay. So, for example, right, if I do now, by the way, this only works for greater than 1, right? So, well, here let me do it for this example. Okay. So here I have this data set, right, and I have no idea, right. I have no idea what that distribution is called. There's no name for that. Okay, so I want to know, right? I want to know, right? What if I want 2 standard deviations? What can I conclude if I say two standard deviations there? Okay, so I say 2 standard deviations. So z equals 2. Okay, here we go. 1 minus 1 over 2 squared. Okay, 1 minus 2 squared, that is 1 minus 1/4, which equals 3/4 equals 0.75. Okay, so that means 75% of the data will be within 2 standard deviations. Now, if I know that this is a normal distribution, right? Now remember, Chebyshev, we can use any distribution. What the main point I'm saying here is the Chebyshev rule is going to be much more conservative, right? With a normal distribution, we're saying 95%, right, is within 2 standard deviations. Okay, all right. If I use the Chebyshev theorem, right, to the normal distribution, I can only say 75%. Okay, that's guaranteed, right? At least 75%. Okay, but in reality, if it's normal, we know that it's greater than 75. We know that it is 95. Okay, all right. And then so if I want to say, then I can use here I can minus 2 standard deviations. So I can add and subtract 2 standard deviations from the mean. Right. So let me just write it here really quick. 2 standard deviations equals 2 times, let me get it here, 10,014, which equals 20,028. Right, let's create an interval here. Okay, you'll see what I'm doing in a second. All right, so 16,442 minus 20,000, then 28, comma 16,442 plus 20,028. If I calculate that, I'm going to get negative 36,470. Okay, that interval. Okay, so what kind of statement can I make about that? I can say that, well, in the tuition and fees, at least 75% of the schools, right, will have tuition and fees between, right, these two numbers. Now, obviously, we can't have tuition and fees at the negative number, right? Again, these are just approximation, right? These are just estimates. So we would, if we had to make a statement, we would say 0 to 36,470. So the 5-number summary, it just provides a basic, 5-number summary provides a summary of the data set. And these are numerical values numerical measures that we'll learn in chapter 3. So what are the 5-number summaries? Okay, so whenever we say in statistics, the 5-number summary, we're talking about min, Q1, median, which is also Q2, right, and Q3 and max. Okay, common mistake is to include average instead of median. No, so the 5-number summary always means these 5 numbers. Okay, all right. Now, what's the relationship? Well, if we can plot these 5-number summaries in what we call a box plot, right, then it gives us a very quick visual representation of the data. Okay, and this is incredibly powerful and incredibly easy to do. So what the process to do this, right, is you will have a number line. Now this is optional, right? But you have a number line, and this will be to scale, okay? And then you would just mark, all right, here's the minimum, right? And let's say that that's the minimum. That is your Q1. That is your median, right? That's your median. That is your Q3, and then that is your maximum. Okay, so you mark them down to scale, and then on top of that, you would draw your box plot. Okay, and sometimes also known as the box and whisker plot. Okay? Why the whisker plot? Well, because of this, you have 2 whiskers. So here's the box first. Let's do the box. So the box will contain, right? Box will contain the middle 50% of the data, because remember, right, Q3 minus Q1, that is your IQR, interquartile range. That will give you the middle 50% of the data. Okay, all right. And remember, right, why do we care about that? Is because the middle 50%, right, is immune or unaffected by the extreme values. Okay, so it depends on context. Like if we're talking about income, for example, or blood pressure, or we want to understand, what is most people like, right? Then IQR is a good number to have. And then we will draw the lines out to the minimum and maximum, right? And so that will give us our range. Okay, and so visually, right away, we can see how spread out, right, is the entire data set, right, and then what is the middle 50 doing, and where is the median. Okay, now understanding the median or seeing the median tells us, right, if the distribution is skewed, right, if this tail, right, if this tail is very far to the right, the median is here, remember, and the median is not going to be affected by this max, then we can see that it is skewed right. Okay, vice versa, if the median is not in the middle, if the median is over to the right, then we know that it is skew left. Okay, all right. Now, let's take a look at a data set that we've been working with. We've been working with for a while. Oh, this is 5. Okay, so this is the data set we had, and we already calculated previously Q1, Q2, Q3. Okay, so let's build a box plot for the following data set. First thing we need is to write down the minimum and the maximum. Okay, let's collect that. 525, 715. Okay, next, right, let's go ahead and draw the number line down here. Okay, just do a rough sketch. Right, approximate to scale is fine. Now the way you do the way I would do this is I would go, well, my minimum is 525. So you know what? I'm going to start at 500, and I'm going to do approximate equal distance 600. 700. Oh, that's not what I want. Excuse me. Let me fix that for just a moment. Okay, that's what I want. So I make approximately equal distance marks, and I want 50, or I want each mark to be considered 50. And then I'm just going to fill in my lines where my 5-number summary is. So go ahead and give it a try. Pause the video, try yourself, and check your answer when you're done. Okay, all right. So this number is optional, right? But I just want to illustrate where the numbers, approximately where the numbers go. Obviously, if we had graph paper, this will look even better, right? More to scale. Okay, but but this gives us a nice visual, right? Here's my min, right? Here's my Q1, median, Q3, and my max. Okay, so with these 5 numbers and I plot them all here, right? Then I can see that, oh, this distribution is skew right, because the median is here, the max is all the way here. So if I had the histogram, which I don't, but let's say if I had the histogram, it will probably look something like this, right? The tail will go to the right, right? So I get a sense of the distribution, right? And I also know that most of the, or half, the middle 50% is between 545 and 625. So this is a really quick figure, right, that allows you to summarize, a lot of data. And what is also popular, right, is you can compare these side by side. So you can see that because it doesn't go up, it doesn't go or the data set, right, the graph doesn't, it takes very little space, right? So you can compare it between populations. You can have one population here, one population here. You can have multiple populations, and instantly you can compare the distributions between different populations. Okay, all right. So that's all make it, and just that's what makes this very powerful. Okay. Okay, outliers. Now, outliers are a little controversial. Okay, so first, what is an outlier? Outlier is an unusually small or large value in a data set. That is the formal definition. The problem is, what is unusual? Okay, so data are not perfect, or I should say, the data that in practice when we collect data is usually not perfect. There might be a lot of errors, right? That's that occurs during the during the data collection process. Okay, now and that's typically the only reason why we need to care about, or we should pay attention to, outliers, just extremely small or extremely large value. Okay, so something that just might look out of place, right? So for example, right, you could just somebody like incorrectly recorded, right? You added an extra zero, or you put the decimal in the wrong place. Right? So that could be an incorrect recorded data. Okay, a data value that is incorrectly included in the data set. Right, so let's suppose that you want to measure heights of elementary school kids, right? And then you ended up measuring the coach as well. Okay, so that's you should not, right? So all of a sudden you're among fifth graders, you have a data point that is 6'8", right? That is really weird, right? And then and also now also you could be corrected, it could be a correctly recorded data value. Okay, so so you could have a kid who is 6'5", 6'8", right? Probably Yao Ming in fifth grade, right? He probably was that tall. Okay. Now for the first two reason, of course you want to take out those data values, right? If you have something extreme that is not supposed to be there, you want to take it out. The third reason here is kind of controversial. Me personally, I don't think you should exclude. You better have a pretty good reason to toss out observations that just because it is extremely large, right? You shouldn't just toss it out because it is extremely large, right? Because you just wanted to make your data better to work with. Okay. And again, this is just personal technique. What is the preference, or are you going to lose your job, right, because the data is not nice, right? Okay, so anyway, up to you to decide. Unfortunately, right, if you just given the data set, often you don't know if it's either an incorrect data value or is it actually correct, just an extreme value, right? You can't tell the difference after the fact, right? Between these two, right? When you see it an extreme value, right? Somebody who is 6'8" among elementary school kids, is that the wrong entry, or is there actually a student that has a height of 6'8"? Okay, and so for that reason, and that's the justification, then as a general rule, people can say, okay, I'm just gonna toss out all of the outliers. Okay. All right. Again, that's up to you, right? If you want to do that. Now, so here I'm going to just give you a simple definition of ways we can identify outliers, and this is the generally accepted version. Okay. So, right. So basically, we want to find an upper limit and a lower. I want to find an upper limit and a lower limit. So basically, any observation that's below the lower limit will be tossed out, considered outlier. Any observation above the upper limit will be considered an outlier, and we'll toss that out. Okay, the calculation is very simple. 1.5 times the IQR, right? IQR below quotile 1, below Q1, not the min, right? Obviously, because we don't, we don't want to, nothing is below min. So we're looking at Q1. Okay, so for example, right, let's calculate the lower limit and the upper limit for the data set above. Okay, so first we need our IQR, right? IQR, which is Q3 minus, here I'll write out, Q3 minus Q1, which equals 625 minus 545. Okay? And so in this case, this equals 120. Okay. Next, so our limit. Well, here let's do our bound. Right, is going to be 1.5 times this 120. Okay, which will be, right, 1.5 times. Oh, sorry, that is not 120. Excuse me. Let me fix that. Okay, sorry, that is 80. Okay, so this is 80 here, right? And that is not 120. So now I got to take 1.5 multiplied by 120. Oh, sorry, multiplied by multiplied by 80. That's 120. Okay, so that would be 120. Okay, and then to find the lower bound, so lower bound or lower limit, right? Lower limit equals Q1 minus 120. Right, which in our case would be 545 minus 120. Right? Here, let me set it up. And the upper limit, okay, will be Q3 plus 120. Okay, all right, equals, in this case, 625 plus 120. Okay, and pop that in the calculator. Okay, and I get 425 and 745. Lower bound, upper bound. So basically, right, any data, any observation that is smaller than 425, we will consider it an outlier and throw it out. Any observation above 745, we will consider that an outlier and throw that out. Okay. A quick glance at our data set here. Right, there is no values below 425 or above 745. So we have no outliers. We have no outliers. No outliers here. Outliers in our example. Okay. All right. Now here is summarizing data for two variables. Now this actually showed up in your textbook in chapter 2. Okay, but I wanted to focus more on single variable, and then after we get familiar with how to deal with single variable, then we can add how to summarize data for two variables in this case. Okay, now most of the stuff or some of the stuff, right, we will come back and visit it in later chapters on regression analysis. But right now, right, just some basic concepts here. Cross tabulation. Now this is the most popular method of summarizing a relationship between two variables. Okay, so cross tabulation could be used when it doesn't matter, right, if one's categorical and the other is quantitative, or they're both categorical or they're both quantitative, right? So it doesn't matter. So first we just organize things in terms of a matrix. So here we have observation, we have data on homes, okay, and then there is two variables. So two variables here, right, for each observation. Okay, two variables for each observation. Right? And then what are the two variables? One is the type of home style. So this is categorical data, right? The home styles, we have colonial, log split, A-frame. Now, the other variable is price range. Okay. Now you might be tempted to say that this is categorical, right? Or sorry, you might be tempted to say that this is quantitative, but this could be considered either, right? Because the fact that we are putting all houses under $250,000 in one category, this becomes the category, right? So this is so you can interpret this as both categorical data and quantitative data. Okay, so we have two variables for every observation, every house, right? How do we present that? How do we summarize that? Well, first, right, so we have the number of homes that's in each style and price category. Okay, so inside, right? So inside is the union, okay, what we call it. So for example, right, there's 18 here, right? That means there are 18 homes that are both colonial style and under 250,000. Right here, there's three. They are three homes that is a A-frame style and above 250,000. Okay, the now when you these marginal, right, these marginal summaries are simply the totals. Okay, so 55, right, 55, that will be represent the total, right, total houses above 250,000. Okay, just adding across. 45 will be, there will be in our data set, there will be total of 45 houses above above $250,000. Okay, on the bottom, the same idea, right? This is 20, so this is the total number of houses that has the log style. Okay, and when you add across, right? So it's pretty intuitive, pretty simple. You're always adding across, right, and adding down. Okay, always adding across, adding down. Right? And then, so here, right, these two add up to be the same. This is total sample, or sample size, I should say. Okay. All right. Cross tabulation, we have a percentage, right? So this is less common, right? You actually don't see this that often, but you might once in a while. So let's talk about it here. Okay. So basically, you're converting, right? You basically are converting the rows and the rows and columns into percentages. Okay, so let me give you an idea what that is. Okay, now because we're converting it to percentage, okay? Then you have to pick a row or pick a column to fix. So when it's row percentage, you fix, okay, fix the row. That's what row percentage mean. Oh, sorry, I can't see it there. You fix the row, okay? In column percentage, you fix the column. Okay? And fix the column. Okay? So that's why you can't have one graph that has both row percentage and column percentage. Okay, the calculation is different. All right. So here, right? So what do we mean by fix the row? Let me explain. So here we're gonna need this top part here. Okay, so I want to know, right? I'm fixing the row. I want to know, right, of the colonial houses, right? What percentage of the colonial houses are less than 250,000? Okay, and so the way I could calculate that. So here, let me put a box here. Okay, let me do the calculation. So the way I would calculate that, right, is to do 18 divided by. Okay, so I'm reading here, right? 18, right? There's 18 houses total, right, that are below 250,000, but that is 18 out of 55, right? There are a total of 55 houses, right, below 250,000. I want to know, right, what percentage of that is, or what percentage of that is colonial. Okay, notice I'm fixing the row. I'm holding the row constant, so that is 55. Okay, so I'll go ahead and put that in the calculator. Okay, so we get 0.327, right, or 227, or we can say 33%. Okay, so that's 33%. Okay, now and then so here, right, we would just calculate across like this. Okay, so go ahead and give it a try. I'm going to fill in. You can pause the video, and I'm going to fill in the answer here. Check your answer when you're done. Okay, if you did it correctly, that's what you should get. Now, I'm doing some rounding. Okay, I am definitely doing some rounding. And so I'm going to want to add across, right? Since this is percentage, right? Since all this is percentage, then the total here should be 100. Okay, should be 100. Now, if you do add all that up, what you will find is I get 101, which is close enough to 100. Okay, and that all that has to do is because I'm choosing to round, I don't have enough space here to write the decimals. Okay, if you add all that up, let's give that a try. 27 plus 31 plus 36 plus 7, and you can also get 101. Okay, so 101, which is basically close enough to 100. Okay, so that is rounding, right? And either of those numbers, right, should be fine. Although you probably, when you're presenting it, you probably should write 100 just to indicate that you capture all of the percentage. Okay, fixed column. all right, or column percentage, right? We just simply fix the column. So here, right, I always do, well, let me do log, right? Suppose that I want to find, right, among all the logs, right, so there's 20 total. Oh, here, let me bring this down, right? Among all the logs, there are 20 house logs total, okay? What percentage of the log houses are below 250,000, okay? So if I want to calculate that box there, right, it will be 6 over 20, okay? 6 over 20, 0.3. Okay, convert that to percentage. I am going to get 30%. Okay. All right. Go ahead and do the rest. Okay. Again, I am dividing according in using the column or the column summary here now. All right. So go ahead and try it on your own. Pause the video. Check your answer when you're done. Okay, so that's what you should get, right? And then instead of, with row, we add across to make sure that we have the total 100%. With column percentage, we add down to make sure we have the total 100%. Okay, and then just keep in mind, yes, you might be a little bit off because we did do a bit of rounding here, but it looks like, right, if we add down 30, 70, 100, 54, 46, 100, 80, 20, 100. All right, it looks like the rounding didn't affect our answer all that much. Hey, graphical methods to illustrate, summarize two variables. Now, one of the most important, maybe not important, but common reason that we want to summarize two variables to understand their relationship, right? The relationship between income and race, eggs and cholesterol, right, and so on. Okay, and so and there are many ways, right? There are infinite number of ways you can do this. The most useful, right, I think, and also the most popular, probably, is a scatter plot and a trend line. Okay. Now, scatter plot or scatter diagram, right? The graphical representation between the relationship of two quantitative variable. Okay, so these are only work with quantitative variable. Okay, or at least is more useful with quantitative variable. So for example, let's say that I have income and a student's what if I have data on years of education and income. Okay, so I can have for every observation, right? For every observation, I have, right. Let's say I have in the x variable, let's say I want to years of education. Okay, so this is 16. So that will be somebody who has a bachelor, who finished a bachelor's degree. Okay, and then for the y variable, so here's my x and here's my y. Right, I want to try to explain, right, their income. I want to use this. I want to see the relationship between income and education. Education and income. Okay, so their income could be, let's say that this person, right, could be I'm just making numbers up here, right? 54,000, right? Or the next person, right? The next person could also have 16 years of education, but their income could be $65,000. Okay, all right. And the next person, let's just add one more, right? For funsies, right? They have 14 years of education, right? And their income is $36,000. Okay, all right. So what is a scatter diagram? So a scatter diagram will have an x and y. By the way, you can easily, right, if you like to, you could flip the two around. So you can let this be y and this be x. Okay, nothing is stopping you from doing so. Right? And so, for example, the first one will be 16. Right, so x would be 16 here. We can say this is 16, and that is 54,000. And here is 16, and that will be the first observation. The second observation, we can have 16. We have 16 as well, but then instead it's 65,000. The third observation will be here 14, right, and 36,000. Okay, so that will be down. That will be down here. Okay, and you can have here we go 36. Let me just add that. All right, and you can have a lot more. Right, so you might imagine, right, if you plot them all out, right, that is the scatter diagram that you might have. Okay, now what is a trend line? Well, a trend line is approximation of the relationship. It is a straight line. A trend line is always a straight line. It's never a curve, right? And you basically just draw a line that you believe it illustrates you believe that it illustrates the relationship between the two. So if I'm observing that the relationship goes like this, it seems like the higher the education, right, the higher the income. I'm just going to draw a line that I think best fits the data. Okay, so that will be my trend line. Trend line right there. Okay. All right, now once you have the scatter diagram, right, and really what we care about more maybe is the trend line, right? So we can use it to describe relationship between x and y. Okay. Now so if we have x and y, x, y here, right? What would constitute a positive relationship? Well, if you have a scatter diagram like that, here's your trend line. Positive relationship, right? Focus here is the slope, like the slope of the trend line. If it's positive, okay, the slope, let's call it m for slope. Remember your algebra. If the slope is greater than 0, right, that will consider positive, right? What would be considered a negative relationship, right? Obviously, it's x and y. Here you just scatter diagram going down this way, and then so you have a negative relationship. Again, the slope here is less than 0, negative. That will give you a negative relationship. Now, we should say, right, what we mean by relationship here in this context is linear relationship. Okay, we're always talking about linear relationship when we say relationship, right? So if what we'll consider a no apparent relationship, x and y, right? So if you have a scatter diagram that kind of goes across like this, so if you were to draw your best trend line, right, it will be flat, right? So here the slope will equal to 0. So there's no apparent relationship here. Okay, so the trend line will be flat. Now, just because there's no linear relationship, it does not actually mean that there is no relationship at all. That's this important thing to note. Okay, so let's say here, suppose that I have x and y, right, and x and y, and then the graph, right, looks like this. The scatter diagram looks like so. Okay. Now clearly there's a relationship. Right? Remember your algebra that we call that a quadratic. We call that a quadratic equation. Okay? That is clearly there is a relationship there. But however, if you were to draw a trend line for that scatter diagram, right, then the trend line will be flat. Right? Then it would appear that there is no relationship. So when we say no relation, we should be clear. Right? It should be no linear, right? No linear relation or relationship. Excuse me. Okay. All right. Okay. Now, in statistics, we focus a lot on linear relationships, right? And so a lot of times, just out of convenience, we will not say linear. We will just say relationship. In more advanced or in like things like a numerical analysis, right, or nonlinear models, right? That's something you can do in graduate school, right, and such. Then you can expand, right? You can then really kind of talk about this type of relationship. Okay, but for now, right, we will stick with a linear relationship only. All right, so let's do an example here. I have the number of interceptions and the point score, right, for this football team. Okay? And by the way, this is each game, right? So I have a total of 1, 2, 3, 4, 5. I have 5 games, right? Or I have 5 games, worth of data. Okay, so I want to create a scatter. First, I want to create a scatter diagram. Okay, now to do a scatter diagram, where's my ruler? Alright, so to start a scatter diagram, I want to make my axes. Okay, and so let's say that I'm more interested in points, and I want to use the number of interceptions to explain the points. All right, and of course I could choose. I could flip it around. I could make the interceptions y if I wanted to, and the points x if I wanted to. Okay, but when we talk about relationship, often is useful to kind of think about what is it actually you're interested in. Okay, or which variable are you more interested in, right? Okay, so we're gonna do we're gonna put x here, and the interception be the x, and the points be the y. Let's draw the x line first. Okay, to draw the axes. All right. Okay. Okay, so here is the x, right? Here's our x, that's our number of intersections. And the minimum is 1, the maximum is 3, so that's pretty easy, right? 1, 2, 3. Okay, easy peasy. Okay, now, number of points. So my y is going to be the number of points scored. Okay, and so it start out, we can see that it starts at 14, right, and it ends at 30. So that's the minimum and the maximum. Now, if I was simply to draw a line here and start at 0, okay, then the bottom of the bottom of the graph, right, will have no data point, no observation, and then all my graph will be up on top here. Okay, all right. That's not a very efficient use of the space. Okay, and so we say graphing is as much art as it is science, right? So we're going to take some liberty here. So I'm going to make a break here, right? And then I'm going to draw 2 lines, right? So the 2 lines here indicate that there's a skip, right? There's something that skip here. So I'm going to start at 0, so 0, and then I'm going to here go ahead and do 14. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to go ahead and I'm going to take the liberty, right? So I'm going to say this is 14, 16, 18, 20, 22, 24, 26, 28, and 30. Okay, and now I can fit all my graph right here, right? And I don't have any wasted space, right, in my graph. Right? If I didn't do that, then obviously I'll have a big I'll have a big blank space on the bottom here. Okay, and I'm gonna go ahead and just do one by one. Game 1, 1 interception, 14 points. Right there. Game 2, 3 interception, 24 points. Okay, just do the best you can, right? To do that, right there. Okay, and so on. Go ahead and do those 5 and check. Pause the video and check your answer here when you're done. Okay, third game, 2, 18. Fourth game, 1 point and 17. Okay, so 17 approximately there. Okay, and finally the last game, 3 interceptions and 30 points. Okay, all right. So that's my scatter. That is my scatter diagram. Right. If I want to do a trend line, I want to draw a line that best fits. By the way, there is more than one way to determine the trend line. Now, right here, we're just gonna go by looks. Right. So I'm gonna draw a line that we think best fits this data. Okay. In later chapter, I think chapter 14, we will develop a more rigorous method of actually developing this line. Okay, so obviously here, right, the slope. Okay, we don't know what the slope actually is, but the slope is going to be positive. So there is a positive linear relationship between the number of interceptions and the total points scored in a football game, at least for Panthers, at least for this football team. All right, so scatter diagram and trend lines are they are very convenient and fast way to graphically represent relationship between 2 variables. Okay, now, but we would still like to develop a numerical measure between the 2 variables. All right. All right, so how do we go about doing that? Well, the motivation is quite simple, right? The motivation is this, right? So we want to know, right? Want to know, right? I want to know that when x increases, right? How does y, right? What happens to y, right? And vice versa, right? Or not vice versa, but when x decreases, right? What happens to y, right? And we want this to be average. Now we don't, like we said earlier, like the example we give earlier, right? Education and income. Right? Yes, there are going to be some people who have a lot of education, right, but doesn't make a lot of money. Okay? But what we're looking for is a trend, right? What we're looking for is overall, right? What is the relationship? Usually, when x goes up, right, what happens to y? When x goes down, and what happens to y? Okay. Now the motivation, to simplify and without going too deep into the math, right? One of the clever tricks we can do is deviation, right? We can look for signs. Look at signs. Okay. So remember, right? So we have x. Let's say we have our x variable here. Okay. Now remember, right? Right. Okay. So here, just bear with me. So let's suppose that x bar is in the middle. So that's the average, right? The average is in the middle here. Okay. And then here is x1, right? And here is x2, right? And x3 and x4. Okay. And so obviously I can take the deviation, right? So if I take, right, xi minus x bar, right, then I'm going to get positives here, positives, right, and negative and negative. Okay. I'm gonna get the signs. Okay, positive, positive, negative, and negative here. Okay, now let's look at the y. Okay. Oh, I should mention. Remember, every observation will have. Right, here's my list. Here's my observations. I have x1, y1, right, x2, y2, right, and and so on, xn, comma, yn. Right, so every observation, I have two variables, x and y. Okay, so one of the technique mathematically that I can try to calculate, right, this relationship that I want, right, what happens when x goes up, right, what happens to y, and x goes down, what happens to y is, I can compare these two, right. Right? I can see what happens. So let's say y1 is here, right? And then y2 is here, right? And then y3 is here, y4 is there. Okay, so I can measure this, right? And I can measure yi minus y bar, right? And now here, this is going to be positive, positive, and there'll be negative, negative. Right? Okay, now here's this thing. So look at what happens here, right? When the x is below, so here, right, when x is below x bar, right, y is above y bar. Okay? And when x is above x bar, y is actually below, right? Y decreases. So if this is the data, right, if this is a relationship, then what we have here is a negative relationship. Now, I can calculate that by multiplying two, right? So if I multiply these two, right, for every data point, meaning if I multiply xi minus x bar times yi minus y bar, right, is either going to be greater than 0, less than 0, right? All right. Well, positive or negative, or at the very extreme events, right? Equals 0. Okay, but typically don't deal with that. What we care about is if it's gonna be positive, or if it's gonna be negative, right? And so in this case, right? So you can see here clearly we have a negative relationship in my example here. Right? Every time when an observation is below the mean, the y value for that same observation is above the mean. So it has a negative relationship. And look, what happens when you multiply a positive times negative? You get negative, right? What happened here, right? You get a positive and you multiply positive and negative. You also get negative, right? And so now we can draw a matrix, right? That is kind of on our x and y diagram, right? So we can have if I divide, okay. Now this might, it takes a little bit of thinking. This is not an easy concept, but that's okay. You don't have to understand this concept completely. You can just use the formula later. But I just want you to know what motivates this. What motivates this? So you have my x and y here, okay, and then I do. Let me draw a line. Let me draw a cross in the middle here, right? And let's suppose my scatter diagram will look like this. Okay, for xi minus x bar, right? If I multiply these two, every observation in this corner, right? Oh, I should say, excuse me, x bar is here, y bar is here. Okay, every observation in this top corner, what's going to be the value? The value will be negative. Every observation in this corner, right? In this corner, right? If I multiply, right? Because here, yi minus y bar is negative. xi minus x bar is also negative. Negative times negative, I'm going to get positive here. Okay, and here, same idea. Xi minus x bar is positive because I'm on the right side here. And yi minus y bar is also positive. So I'm going to get a positive value here. Okay, and then here, I'm going to get a negative value. Try some numbers on your own, right? This is not intuitive right away. It will take a minute. But if I can gather the relationship, meaning adding them up, right? Adding them up, right? Then that will tell me the trend, right? That will give me a numerical measure, right? That will give me a numerical measure of the relationship between the two variables. Okay, let's practice an example here, all right? So I have two variables and I have every observation, right? So this is the golfer. Okay, so this is the golfer and he's looking at different games. So he has placed 1, 2, 3, 4, 5, 6 games, 6 games here. Okay, and let's say that let's say that he's more interested in more interested in his average score. Okay, so average score. So we're gonna call this x, right, and this is y. Again, doesn't matter. You can choose this to be y if you want, right? It will work out the same, okay? Or at least the relationship will be the same, so that will not change. All right. Now, like I said, all right, if you don't really quite, take a moment, right? Take your time with this, trying to see if the intuition, I think it's pretty valuable. But if not, that's okay. If you just want to memorize or learn how to use the formula, that's fine too. So basically, using this using this motivation, right? We developed this thing called the covariance. So covariance is a numerical measure of the linear relationship or association between two variables. Okay, and here we see, so for sample, and let's just do it for sample. Again, in reality, we will never really calculate the population because we never have the population anyway, right? So we're always going to use this. The population, this is the formal definition, right? That's what we're trying to estimate. Here is our estimator, like, in context. Okay, all right. So basically, the idea here is, right, we have this product xi minus x bar times yi minus y bar. Okay, so we want to do that for every observation, and then we're just gonna add them all up. Okay, so let's get that first. Now I have things written down this way, so let's do this by hand, and I will show you later on how to do this on Google Sheet. Okay, but I think it's good to know that get your hands dirty a little bit. Okay, so the best way to do this through the column method. So I'm going to create basically I'm going to create 3 additional columns. I'm going to create 3 additional columns here. Okay, the first column is going to be xi minus x bar. Second column will be yi minus y bar. Okay, third column will be the product of the two, xi minus x bar times yi minus y bar. Okay. Okay. All right. And I hope you see now, right, why the column would help. Right? The column method will help because now it makes organize the data very convenient. So in this column, I'm going to take every x value minus the average. Okay, so then that tells me I need to calculate my average on the side. I need to do that separately. So I did that earlier already. Okay, you can pause if you want to do it yourself. But the average for x is 266.93. The average for y, right, it is 70. It is 70. Okay. All right. So I want, right, to subtract this. So here we go. 277.6 minus 266, and that is going to give me 10.57. Okay. The next one will be negative 7.43. Okay. I'll finish that in a moment. Then for the y, 69 minus 70, that will be negative 1. Okay, all right, negative 1, 71 minus 70, that will be 1. Okay, all right. And then finally, we will multiply across. Okay, so now the difference between this and sample variance, which looks very similar, is that I'm not squaring anything, right? Because I actually want the negative values and the positive values, right? Because those are information that tells me something. Okay, so I'm going to multiply across. Okay, multiply across, and that's going to give me negative 10.57. This will give me a negative 7.43. Okay, and then so I'm going to do I'm going to go ahead, all right, and fill in the rest. Okay, pause the video if you want to try on your own. Check your answer when you're done. Okay, all right, so I got all that, right? And here, notice, right? So I want to, so see, the product here tells me, right? The product here tells me that on average, all right, on average, which quadrant, right? Which of these four corners is the data occurring? Okay, is it occurring in these two or is it occurring in these two? And since most of them are negative, right? That tells me the data is going downwards like this, right? It's a negative relationship. Okay, all right. And if you know anything about golf, right, that should make sense, right? The further distance that you hit, the lower your score, right? In golf, you actually want low score. Okay, all right. Okay, so in golf, lower the score, the better. Okay, all right. So let me write down my formula, right? My standard or covariance, my sample covariance of x, y. Now, it always a good idea to add the subscript x and y, right? Because if you don't add this, right, then you can't distinguish it between the standard deviation or the sample standard deviation, right, for x and for y. Okay, all right. So make sure you use the subscript, right, to enter. Oh, sorry, you can't see it there, right? Make sure you use the subscript here, right, to indicate, right, that this is a covariance. So by writing this is your sample covariance, right, for x and y. All right, sample covariance for x and y. Okay, that's my shorthand for and. You feel free to borrow that. Okay, and the formula goes like this: summation xi minus x bar times yi minus y bar on top, and on the bottom is n minus 1. Okay, we need to have the n minus 1. All right, don't worry about it for now. I will explain later what that means. Okay. All right, but you don't need to know, just follow the formula. Okay, and so on top here tells me that I want to add this up. So you go ahead and you sum up the last column here. Okay, so if you did that correctly, you should get this. Okay, all right, now my sample is, I have 6 game here. My n equals 6, then n minus 1 will give me 5. Okay, and so my covariance is negative 7.06. Okay, all right. That's it. Now, a couple things, right? Covariance by itself does not tell you the magnitude, right? It only tells you the relationship. Okay, so there's this here covariance. Let's make a note of it, right? Covariance are only tells you, right, relationship. Right? It does not tell you, right? Does not tell you how strong the relationships are. Okay, it does not provide you context, right? So you could not say -7. Oh my gosh, that seems like a lot, right? There's no strength to this to this number. So only negative, right? So if it's negative, then only thing you can say is there's a negative, right? That is a negative. Oops, excuse me. Negative relationship. Okay, all right. Now we want some context, right? We want to be able to measure how strong, right? How strong is a relationship? Okay, so to do that, right? Then we need correlation. We need correlation coefficient. Okay, all right. So correlation coefficient is basically you take the covariance and you scale it. Okay, now coefficient, right? It's always between -1 and 1. Okay, all right. So value that's closer to -1 indicate a strong negative linear relationship. If it's close to +1, then it's a strong positive linear relationship. All right. So to calculate correlation coefficient, you need 3 things. First, you need the covariance. And then you need the standard deviations, okay, or the sample standard deviations. Right? So then you notice here now, this is why it's really important for us to use the subscript. right? So I'm going to write it down again. SXY, this represents the sample, right? Sample covariance, right? For X and Y. S of X, this is the sample standard deviation. S of Y, this represents the sample standard deviation. Oh, sorry, I should sample standard deviation for X. This is the sample standard deviation for Y. Okay. Now go back, right, to just review a bit on how to calculate a sample standard deviation. Actually, here, let me write the formula up here just for you to reference. Right. Remember, it's summation xi minus x bar squared divided by n minus 1. Okay, so you would do that for both x and y separately. Okay, do it by themselves, right? And then use that to calculate the correlation coefficient. Now I did that earlier separately. Okay, so I did that already. Okay, so so I got this. So do this on the side. So I got S of x. So sample standard deviation of x is 8.19. Right, sample standard deviation of y is 7.48. Okay, so again, you have to calculate these on the side. Okay, and now S of xy, we calculated this earlier on the previous page, and that is negative 7.06. Okay, all right. So now we can just calculate the correlation coefficient, or the sample correlation coefficient. It is indicated with the letter R. Okay, R of xy, again, indicate which variables you are talking about. Right? And so this is S of xy over S of x times S of y. Now plug it in. Negative 7.06 over 8.19 times 7.48. Okay, all right, put that in your calculator. You should get 0.115. Right? Or negative 0.115. Standard deviation is always positive. Okay, so that will always be positive. So really, what gives the sign, right, will be the numerator. Numerator will always give you the sign. Okay, and now, right, so remember, so the sample correlation, right, the sample correlation coefficient is always between 1 and negative 1. So here we have negative 0.115, so that's about over here, negative 0.115, right? Okay, not that strong, right? Now we don't have any actual names or say how strong it is, but we just say this doesn't seem very strong, right? If it's closer to negative 1, right, it will be it will be stronger here. Okay. One more note, right? What you will see here is whenever we're calculating the sample, we always use just regular English letters R, right? But these are estimators, right? These are samples, right? The population parameter that we're interested in is expressed by Greek letters, right? So this is rho, like this thing here, looking thing here, that is a rho, right? RHO, right? If you wanted to pronounce it, okay. And same thing as here, right? For our covariance, our sample covariance is expressed with the letter S, right? But the population parameter that we're interested in to estimate is sigma of xy, okay? Sigma of xy. All right. Okay, so that is all for measurements, or that is all for handout 3.3 and associations between two variables. Okay, like I said, we will revisit a lot of these things back in chapter 14 when we talk about regression analysis.